All right, so moving on to chapter 8. Chapter 8, the first few sections of chapter 8 talk about complex numbers. Sorry, my children are talking in the background, and so you may hear a little bit of interruption. But anyway, so chapter 8, the first few sections are about complex numbers, and then the latter part of the chapter is about polar equations and parametric equations. So to be honest, those last two sections really don't have much to do with with the first four sections, except that the way that we treat complex numbers is sort of similar to the way that we treat polar coordinates. And so we'll see all this when we get to that a little bit later on. Sorry, I just had to tell my kids to be a little bit more quiet. Anyway, so so let's get into complex numbers. Now, this is mostly going to be review because I know that you've seen complex numbers before. You should have seen them in Math 35. Anyway, even if you haven't, I'm sure you've seen complex numbers at some point in the past. So we're just going to review complex numbers a little bit. And in this particular section, you're probably going to be thinking to yourself, okay, but what does this have to do with trig? Well, we'll see in 8.2 in the next section how we deal with complex numbers in polar form. And to put complex numbers in polar form requires a little bit of knowledge of trig. And once we have complex numbers in polar form, then we can do a lot of really interesting and cool things with complex numbers. Even still, you may kind of question, well, but like, there's a lot of cool things we could do with trig. Why are we talking about this particular concept? And the reason for that is, complex numbers turn out to be hugely, hugely important in mathematics. They really round out our discussion of algebra, and we will talk about all of that when we get into like de Moivre's theorem and stuff in like 8.3, 8.4. So let's get into it. So I'm going to start off by attempting to draw a sort of Venn diagram with all of the different sets of numbers that we typically talk about. So when you're a kid and you're first learning how to add and subtract and all of that stuff, the number set that you're working with is the natural numbers. So the natural numbers. Those are the positive whole numbers. So like 1, 2, 3, and so forth. While you're doing all of that, at some point your teachers probably throw 0 into the mix. So when you take the whole numbers and you put 0 in the mix, then you've got the whole numbers. So the whole numbers are just the natural numbers, but with 0 added in to the mix. And then at some point around maybe 6th or 7th grade or something like that, then you start talking about negative numbers, negative whole numbers, and those are called integers. So all of the positive and negative whole numbers are called integers. So the integers would also include, all of the negative numbers, and then, of course, 0, and then the positive whole numbers as well. Now, along the way, at some point, maybe in 3rd, 4th grade, something like that, you also probably started talking about fractions. And fractions are, when you add fractions into the mix, then you've got what are called the rational numbers. So the rational numbers include all of the they include all of the integers, but in addition to the integers, they also include the fractions like 2/3 and -5/12 and stuff. Now, there are other kinds of numbers though. You may be aware of the fact that not every number can be rewritten as a fraction. So there's a bigger set of numbers here. That bigger set of numbers is called the real numbers. And the real numbers, in addition to the rational numbers, the real numbers also include irrational numbers, like the square root of 2, or pi, or e, right? Euler's number, e, right? So, so the real numbers also include all of these kind of irrational numbers. And an easy way to tell a real number from a rational number is to change these into decimals using a calculator or something. If the decimal number is non-terminating and non-repeating, then it's irrational. If it's a terminating decimal, or if it's a non-terminating decimal but it has a repeating pattern, then it's a rational number. It's actually, and I say that that's an easy way to tell irrational numbers from rational numbers, but in reality, that's not always a simple task. But anyway, so the real numbers include all of the rational numbers, right? So all the rationals, but plus all these irrationals as well. Now the complex numbers include an even bigger set of numbers. And outside of the real numbers, there's this set of numbers that you may have heard of called imaginary numbers. Imaginary numbers are numbers that involve the imaginary unit I. So numbers like 3i, or just I by itself, or negative 5i. Those are all imaginary numbers, okay? The complex numbers are the real numbers plus the imaginary numbers plus any linear combinations of real and imaginary numbers. So the complex numbers sort of encompass all of this stuff. So the complex numbers encompass all of this. And so the complex numbers, in addition to including purely imaginary numbers or purely real numbers, they also include like a mix of numbers, like 3 plus 2i would be a complex number. Or, you know, they could be even, you know, stranger than that. I guess you could have something like pi plus I times the square root of 7 or something, right? So those would be complex numbers as well. And the complex numbers, the buck stops with complex numbers, okay? Mathematically speaking, we don't really talk about sets that are bigger than the complex numbers. And the reason for that is because the complex numbers contain all of the solutions to all of the possible polynomial equations that could be thrown your way. So there's no need to define a larger set of numbers. It's like once you get to the complex numbers, it's like the buck stops there. That defines all of the possible numbers that we could need in our calculations. It is a little bit of a strange concept, this imaginary unit thing, though. And so you may, to maybe talk about that a little further, you may recall that the imaginary unit I is defined to be the square root of -1. And so it's a strange thing to wrap your brain around, because you think, well, the square root of -1 can't be 1, obviously, because 1 squared is +1. But it also can't be -1, because -1 squared is, again, +1. So square root of -1, you know, what is this thing? Well, we define it to be the number I. We just define this number into existence. And that's, I think, where the name imaginary comes from. But imaginary is really not a very good name for this. And I don't mean to, oh, this should say recall. Recall. Anyway, I don't mean to shatter your world too much, but when people say like, oh, these are like, why do we talk about imaginary numbers? They don't even exist, right? And it's like, well, yeah, sort of, but actually also no. I mean, there's no reason to believe that the number 1 is real, while the number I is not. Well, see, and real is a bad word for this too. Maybe I should say there's no reason to assume that 1 exists in reality, but that I does not exist in reality. I mean, have you ever bumped into the number 1 on the street? You know what I mean? The only reason you know about these numbers up here is because you've invented them in your mind. You've kind of, you know what I'm saying? So these numbers in this number system, they're all kind of an invention of the human mind. Although there is some debate about that, right? A lot of mathematicians, you know, kind of tend to believe that no, there's something more to it than just human invention. And there are reasons for their beliefs, but we're digressing quite a bit here, so I'm not going to get into it. But the moral of the story is it's all just really a system that we sort of invent to make sense of the world around us. And so there's no reason for us to sort of cast out the number I just because it's something that's maybe a little bit uncomfortable to us at first. When we throw this number into the mix, we get a lot of really nice properties. Another thing to kind of recall before we start looking at some examples is that whenever you see the square root of a negative number, like square root of negative a, and here I'm assuming that a itself is positive, so that negative a is negative, right? So whenever you see the square root of a negative number, you can rewrite this as I times the square root of that number, okay? And so these two facts taken together, they sort of encapsulate all of the behavior of complex numbers, well, imaginary numbers, but then by extension, complex numbers in general. So what I'm going to do is take you through several examples. Oh, so many examples. We're going to go through a bunch of examples. And I'm going to go through them kind of quick because, again, I feel like most of this is probably just review for you. So just trying to jog your memory here. Let's simplify a bunch of stuff. And I'm not going to say this for every single problem. At this point, it should kind of go without saying that you should pause the video and try each one of these out by yourself before you watch my solution, okay? But the first thing I'm going to show you is something like square root negative 25. So let's say that we want to figure out what square root of negative 25 is. Well, we need to be somewhat careful about the order in which we apply certain facts. The square root of negative 25 would be I times the square root of positive 25. And square root of positive 25 is just 5, right? So this is I times 5. The canonical way to write that is to say 5i. Okay. Let's do square root negative 17. Okay, same deal. Square root negative 17 is just going to be I times the square root of positive 17. And that's about as good as that one's going to get. Okay. That's as simplified as that gets, and we leave it that way. And I kind of wish that the standard way to write this were root 17i, so that, you know, these things would match. But the reason that they don't is just because if you write it this way, then it's not always clear if the I belongs underneath the radical or not. It doesn't, right? Not in this case anyway. So to avoid that confusion, they just put the I in front of the radical sign. But anyway, so this is kind of the standard way to write down that answer. If we had square root of negative 18. Again, we start off the same way. This is I times the square root of 18. But now square root of 18 we can simplify. If you think back to simplifying radicals, and we've done a fair amount of this in this class anyway, but square root of 18, you think of the largest perfect square that goes into 18, and in this case it's 9, right? So we say this is the square root of 9 times 2. Square root of 9 is 3. So this is going to be 3i times the square root of 2. And that's how we write down that answer. Now, I'm not going to insist that you show all of these steps. If you're comfortable going straight from square root negative 25 to 5i, that's fine with me. I'm totally fine with that, okay? I'm just trying to give you some justification here so that you know where I'm getting these answers from. Moving on, let's talk about how multiplication works. So if you have something like root negative 5 times root negative 5. Now, hopefully your intuition kind of tells you that when you have the square root of x times the square root of x, you should just get x. So in this case, we expect to just get negative 5. On the other hand, your intuition might tell you that when you multiply two radicals, you can just multiply their radicands, right? And so on the one hand, so what I'm about to write down is incorrect, okay? Just fair warning, what I'm about to write down is incorrect. But on the one hand, you might think, okay, so this is square root of -5 times -5, which is the square root of positive 25, which is positive 5. And you could come up with positive 5 as your answer. That would be wrong, okay? The way that we should do this is we should apply that fact about square roots of negative numbers that we just talked about, right? Square root -5 is really I times the square root of 5. I times I is I squared. Root 5 times root 5 is root 25. I squared, you may remember, is just a -1, and square root of 25 is 5. So you get -5 just like you kind of expected. Okay. This way, square root of x times square root of x is always x. Okay. If you're a little confused about why I squared is equal to -1, well, I squared would just be root -1 times root -1, and that we define that to be -1. Okay, and so that way everything kind of stays consistent. So we would not do it the top way; we would do it the bottom way. Same thing goes for division. So if we have root -20 divided by root -5, you might be tempted to think, well, this is just square root of -20 divided by -5, so it's just the square root of 4, which is just 2. But if you do it that way, you're going to be off by a sign. Well, no, actually, you do get. Well, that's kind of interesting. Well, you do get. See, and here I am surprising myself. But you do get positive 2, don't you? This would still be I divided by I times square root of 20 over 5. Yeah, because I divided by I should just be 1. Well, there you go. Here I am looking pretty foolish. But yeah, you do get positive 2 still. Anyway, but that's how that one works. Do I need to show you any more of those? I think you got the idea. I mean, obviously, if you're mixing up positive and negatives, like if you've got, square root -48 divided by square root positive 24, you don't take out an I on the bottom one, right? Because it wasn't negative to begin with. So, but otherwise, I mean, this is just the same sort of thing. So this would be I times the square root of 2. Okay, so that's that. If we were working with something written this way, and this is a pretty common occurrence, especially when you apply something like the quadratic formula, like you're trying to solve some kind of quadratic equation that's not factorable, and so you use quadratic formula on it, you end up with expressions like this all the time. But when we're writing something as a complex number, our goal is to have this in the format a plus bi. This is what we're shooting for. We want it to look like a plus bi, where a and b are real numbers. Okay, so they don't have to be nice whole numbers, but they do need to be real numbers. So they could be fractions, they could involve radicals, okay? But the point is we want it to look like this, a plus bi. What we have right now looks something like a plus the square root of a negative number divided by some other number, right? It's not in the correct format. So we're going to write this in the form a plus bi by doing a couple of things. First of all, we're going to rewrite this as I times the square root of 128. Now it's in the form a plus bi, but divided by 4. So the second thing we're going to do is we're going to split that denominator. Call this -8/4 plus I times the square root of 128 divided by 4. Now it's in the form a plus bi. Okay, this is the format that we really want it to be in. This is what we want it to look like. There's a little more simplifying we can do, though, because, for example, 8 divided by 4 is, of course, -2. Square root of 128. 64 goes into 128, and 64 is a perfect square. 64 goes in twice, right? Square root of 64 is 8, so this is going to be 8i over 4. Oh, 8i, sorry. 64 goes into 128 twice, right? So we would say this is 64 times 2, so the 2 stays there, and the root 64 comes out as an 8, okay? So one more step, and then I think we're there, right? So this is negative 2 plus 2i root 2. That would be a good way to write down the number. I would prefer it to be like this, negative 2 plus 2 root 2i. I think this looks nicer. This is in the form a plus bi, but this is how your book's going to have the answer. So either one of these, right? Either one of these would be fine as your final answer here. Okay, so that's how we're going to shoot for our answers to be. Whenever we're adding, subtracting, multiplying, dividing, simplifying, if the answer is a complex number, then we want it to look like this. Okay, we want it to look like a plus bi. Again, fractions are okay, but it just needs to have a real number plus or minus a real number times I. Okay, and so we wouldn't leave it this way. So with that in mind, let's do some addition, subtraction, multiplication, division. Oh, I'm sorry, I don't want to do multiplication yet. Let me try this again. Let's do, oh, it's the same numbers, 3 minus 4i plus negative 2 plus 6i. Okay, so the trick here is to just treat these exactly like you would treat variables. You know, you can treat I just like a variable. So when you're adding two linear expressions, you combine like terms, right? So in this case, 3 and negative 2 are like terms. That gives us 1. Negative 4i and 6i are like terms. And together they give us 2i. And that's that, right? That's the answer. And notice that our answer is in the form a plus bi. So that's how we like it. We can use the same thing with subtraction, right? 3 minus 4i minus negative 2 plus 6i. Just be sure to distribute the negative sign, right? So we're doing 3 minus negative 2. That's the same thing as saying 3 plus 2, which is 5. And then we have negative 4i minus 6i. Right? So negative 4i minus 6i would be negative 10i. Again, we've got something in the form a plus bi. Okay, now let's do some multiplication. Let's do 3 minus 4i times negative 2 plus 6i. Again, I know I'm flying through these examples, so like feel free to pause the video so you can catch up. Or better yet, pause the video so you can work out the solution yourself before I work it out for you, right? Okay, 3 minus 4i times negative 2 plus 6i. So again, you treat this just like you would treat variables. So you're going to FOIL this, okay? So we're going to do 3 times negative 2, 3 times 6i, negative 4i times negative 2, negative 4i times 6i. And then the thing to remember is that I squared is the same thing as negative 1. So that this is just negative 6. 18 plus 8 is 26. And then minus 24 times negative 1. Okay, well, negative 24 times negative 1 is positive 24. Okay. And then 24 minus 6 would be 18, right? So we've got 18 plus 26i as our final answer. And again, right, we end up, when we multiply two complex numbers together, we end up with an answer that's a complex number, right? We end up with something in the form a plus bi. So this is what we're always shooting for, right? We're always shooting for our answers to look like this. Let me give you another example of multiplication. If you wanted to multiply a complex number times itself, again, you have to FOIL, right? So if we wanted to do 3 plus 4i squared, heaven help you if you say that this is 16 plus 9i squared. That is not true, right? The exponent doesn't distribute across that addition. So that's not how we would work out that problem. We would write it out twice and we would FOIL. Okay, so we FOIL this, we get 16 plus 12i plus 12i plus 9i squared. Right, so similar to this question, and yet so very dissimilar here in the middle, right? So they are not the same. Okay, so here we would get 16 plus 24i minus 9. I'm just going to go ahead and say the I squared is going to change this sign, whatever it is, right? So 16 plus 24i minus 9. 16 minus 9 is 7, right? So 7 plus 24i. Okay, and that's how that works. Okay, so whenever you multiply, you FOIL. The one thing that does work a little bit different with complex numbers than it does when you're just working with, you know, a normal algebraic expression is division. With division, with algebraic expressions, we usually do like long division or something like that. Here we're going to employ a different strategy. When we want to divide two complex numbers, the way that we handle it is we multiply by the conjugate of the denominator. And the reason that we multiply by the conjugate, I mean, I'm sure you've seen this in the past, but the reason we multiply by the conjugate is because what ends up happening is that the imaginary part will disappear, and then you'll just have a real number in the denominator. And then once you have just a real number in the denominator, you can split the numerator so that you end up with your answer in the form a plus bi. So let me show you. In this case, the conjugate would be 5 plus I. So we're going to multiply top and bottom by 5 plus I. And make sure to FOIL, right? Whoops. So FOILing, we would get 15 plus 5i, plus 3i, I apologize. It's 15 plus 3i plus 10i plus 2i squared. And in the denominator, we get 25 plus 5i minus 5i. So you can see that you're going to get that cancellation. In fact, most of the time, I don't even write those middle terms. And then we'll say minus I squared. So simplifying this now, we've got 15 plus 13i minus 2 over 25, the middle terms cancel, plus 1. And now we're almost there. 15 minus 2 is 13, so we've got 13 plus 13i divided by 26. So now all we have to do is write this as a complex number. That means we're going to split the numerator. We're going to call this 13 over 26 plus 13 over 26i. That simplifies a little bit more. 13 over 26 is a half, right? And there's our final answer. But again, notice that when you divide two complex numbers, you end up numbers that when you perform these in the complex numbers, right? So again, kind of goes back to the fact that there's no need to define a bigger set of numbers than the complex numbers. They're totally self-contained in that sense. Okay, let me give you another one of these examples. Let's do 3 over 2 plus I. Okay, Now you're not going to multiply by 2 plus I in this case. You're going to multiply by the conjugate of 2 plus I, which is 2 minus I. Okay, so multiplying through by 2 minus I. In the numerator, we're just going to get 6 minus 3I. In the denominator, we're going to get 4 minus 2I plus 2I cancels. Minus I squared. That's the same thing as saying plus 1, right? So this is 6 over 5 minus 3 over 5I. And those fractions don't reduce, so that's as far as that one goes. So moving a little quicker through that particular example, but that's how that one works. And let me give you one more example of this. So let's say you wanted to do something like 5 divided by I. You might be really tempted to say, okay, so I need to multiply by the conjugate of I, which would be negative I, right? If you think of it, you could think of this like 0 plus I. So then the conjugate would be 0 minus I, which is just negative I, right? And that would work. You could multiply by negative I, and that would do the trick. But you don't need to. You could actually just multiply by I itself in this case, because the denominator doesn't have any real parts. So multiplying through by I, that's gonna already change the denominator into I squared, which we can rewrite as -1, right? So it still does the trick of getting rid of the complex number in the denominator there. So we can call this 5I over -1, which is just negative 5I. And that's kind of an interesting thing, that dividing a real number by I is the same thing as multiplying that real number by negative I. So kind of an interesting fact about these imaginary and complex numbers. I want to give you two more examples of simplifying complex numbers. We might run out of letters. No, we're almost done. When you have really large powers of I, we've talked about the fact that I squared is -1. So we know that I is I squared is -1. Well, what should I cubed be? Well, I cubed would be I squared times I to the first. Well, I squared is just -1. Maybe I should be writing this down. So kind of as an aside, I guess. Again, I'm sure you've seen this stuff before, though. We're thinking about I is just I. Right? I squared is -1. I cubed would be I squared times I. That would be -1 times I, or in other words, just negative I. I to the fourth power, well, now that would be I squared times I squared, which is -1 times -1, which is just +1. Okay, and then we get to I to the fifth, and that's going to be I to the fourth times I. That's just 1 times I, which is just I, and then we're back to where we started. Right? And so this thing just ends up going in a loop over and over and over again, where you just alternate between those four values: I, -1, negative I, 1. I, negative I, I, -1, negative I, 1. You don't need to memorize that, but what that should tell you is that these exponents, right, these powers of I, they're going to be related to multiples of 4. Right? So if you have something that, so if you have some large exponent like 15, you can divide that exponent by 4, and then whatever the remainder is, that's what this expression is equivalent to. So in this case, if I take 15 and divide it by 4, 4 goes into 15 3 times, with 3 left over. So I to the 15th is the same thing as I cubed. Okay, that's what that tells you. And I cubed, of course, could be rewritten as negative I, as we saw over here, right? I cubed is the same thing as negative I. To give you another example of this, let's do p to the, or p. Let's do I to the, oh, I don't know. 27th, maybe? No, I want to do 29. Let's do I to the 29th. So again, we would take 29 divided by 4. 4 goes into 29 7 times with 1 left over. And so I to the 29th is the same thing as I to the 1st. So I to the 29th is just I. This works with negative exponents as well. So if you had I to the negative 3 or something like that, well, how would this work exactly? I to the negative 3. Well, so I guess the way that I would approach this one is I would say if you multiply this times I to some multiple of 4, then you're really just multiplying it by 1, right? So in other words, I to the negative 3 is of course the same thing as I to the negative 3 times 1. But 1 is the same thing as I to the 4th power. So that just gives you I. So I lied when I said I would only give you 2 more examples, because here I am 4 examples later. But let me give you one more. So let's say you had I to the negative 32. Oh, bad example. Maybe we'll say I to the negative 36. So what you want to do is multiply this by 1. But I to any exponent that's a multiple of 4 is equivalent to 1. So if I think about, well, what's a good multiple of 4 here that would make this thing positive? Well, 40, right? Why did I say 36? I want to do 34. I to the negative 34th power. Negative 34th power. So then I wouldn't use 40, I would use 36, right? Oh, I've butchered this. Let me start it again. Let me use a different example. So we'll do I to the negative 42. Why not? Okay, I to the negative 42. So I'm going to multiply this by I to the 44th, because that's a multiple of 4. And when I multiply these out, I'm going to end up with a positive exponent, an exponent of 2. So I to the negative 42 should be the same thing as negative 1. Anyway, you might think of a different way to do these kinds of problems, and that's totally fine, as long as you end up at the same place, right? It still works out. Okay. So after all of those examples, I wanted to just refresh your memory on complex numbers when you are dealing with solutions to equations, because this is really the main reason why we talk about complex numbers. Because as I said at the beginning of the lecture, when you introduce complex numbers, or when you introduce imaginary numbers into your number system, now suddenly you capture all of the possible solutions to polynomial equations that you could ever get. And we'll see more of this, in coming sections. But for now, we can see this with quadratic equations at least. So let's solve a couple equations. Let's do x squared plus 24 equals 0. So go ahead and give the video a pause and see if you can work that one out. Okay, here's my solution. I'm going to start off by moving 24 over to the other side. And then I'll take the square root. Don't forget, when you take the square root, you need to have a plus or minus sign on there. Okay, well, pretty clear. You've got a complex, a complex number, of course, but you've got an imaginary number on your hands here, right? So we're going to say x is plus or minus I times the square root of 24. And as a matter of fact, we can simplify square root of 24 a little bit, right? 4 goes into 24, and 4 is a perfect square. So 24 is 4 times 6, and square root of 4 is 2. So I'm going to call this thing plus or minus 2i times the square root of 6. And that would be my final answer. Or you might give your answer as a solution set. Negative 2i root 6, positive 2i root 6. Okay, so that's that one. Not really much to that. Let's try something a little more challenging, just to remind us how quadratic formula works. I think we saw some equations that required quadratic formula back when we were solving trig equations in the last unit. So go ahead and give this video a pause. See if you could work it out. Sorry. Okay, now here's my solution. I suppose you could try to solve this by factoring first, or you could solve it by completing the square if you really like completing the square. I wouldn't recommend that on this one. Oh, because you've got a 9 out front. That's pretty nasty. If you're going to solve by completing the square, you might as well just use quadratic formula, I think. So let's use quadratic formula. X is negative b plus or minus square root of b squared minus 4 times a times c over 2a. Well, 4 times 9 is 36, so 5 times that is going to be much bigger than 36. So you can tell you're going to get a negative number in here, which makes this a non-real solution. Well, let's see what it is. (36 minus 180). It's negative 144. Oh man, that's beautiful, isn't it? They rigged this for us to be super nice. Square root of negative 144 should be 12i, right? So we're almost there, right? Rewriting this as a complex number, we'd say, or as two complex numbers, really. This represents two different complex numbers, 6 plus 12i over 18 and 6 minus 12i over 18. But we can simplify this a little more. So that's what, 1/3 plus or minus 2/3 I. Okay, and that's that. So your solution set would maybe look something like 1/3 plus 2/3 I and 1/3 minus 2/3 I. And that's that. And that pretty much does it for this section. So again, just kind of a brief review of what you already know about complex numbers. And then in the next section, we'll talk about complex numbers in polar form.